let's talk about the universal law of gravitation. Okay, the universal law or the law of universal gravitation. Doesn't matter how you want to word that, but the universal law of gravitation. Okay, and as I said earlier in the presentation, Newton is the one that spearheaded this whole thing. He's the one that got the body of this all together, uh, being that gravity was a mutual attraction between two objects. So, as the equation goes, we have the force of gravity equals g, which was the universal gravitational constant, and the mass of two objects, m1 and m2, divided by their distance separated squared. Now remember, their distance separated square is coming from the centers of mass of both objects. Okay, so we can take this and let's say, let me put in the givens here. So g, which is the universal gravitational constant, is 6.67 times 10 to the negative 11 Newton meter squared per kilogram squared. Okay, so that is the um, universal gravitational constant, g. We're going to put in one mass one. We're going to put in as, let's just say it's a person. Okay, and we'll say the person is 150 kilograms. And then we're going to do the mass of the Earth, which is 5.972 times 10 to the 24 kilograms. And this person is standing on the surface of the Earth. So their distance being separated is going to be the radius of the Earth. And so that's going to be 6.378 times 10 to the 6th meters. Okay, so these are our givens that we're going to use. So let's plug them in and find out what the force of gravity is. So I say force of gravity is going to be equal to 6.67 times 10 to the negative 11 Newton meter squared. Now I'm going to do this in dimensional analysis. I know you guys love dimensional analysis, just absolutely adore it. So I'm going to use this. Okay, 6.67 times 10 to the negative 11 Newton meter squared per kilogram squared. Now I'm going to multiply by my two masses. Okay, so it's going to be 150 kilograms times my 5.972 times 10 to the 24 kilograms. And then I'm going to divide by my distance squared. Now, the distance is squared, so what I'm going to do is I'm going to do two distances in the bottom. If you square this, you got to square both pieces. So you got to square this piece here, but when you square a power of 10, you're going to multiply the 2 times the 6, okay, to make 12. But I'll do it this way because I think this will be just a tad bit easier. So 6.378 times 10 to the 6 meters, and put one more in here, 6.378 times 10 to the 6 meters. Okay, now take care of uh, our units first. So I got a kilogram and a kilogram, so that's two sets of kilograms. I got two sets of kilograms here, so that cancels out, cancels with these two. And let me just change colors real quick here. Okay, show what I'm doing. Crosses out, crosses out, crosses out. Excuse me. And then I've got meters squared here, meters. I've got meters here, so 2 meters. I've got 2 meters here, so these are going to cancel out, cancel, cancel. Now I'm going to do, remember, I do this thing called the stupid Chisholm trick, And this is my powers of 10. I'm going to take care of my powers of 10 first. One thing with my powers of 10, this right here is a power of 10 also. So 1.50, so this would be 1.50 times 10 to the 2. So let me take care of all my powers of 10. If I'm multiplying my powers of 10, I'm going to add the exponents. I'm going to put this down here and say times 10 in the bottom, and that'll take care of my powers of 10 that are up here. Okay, so that's going to be in my answer. So this is 10 to the negative 11, and I'm going to add negative 11 to 2 and to 24. Well, 2 and 24 make 26, and then minus 11. So this 26 minus 11 makes 15, right? So I got 10 to the 15 up here. Down in the bottom, I've got 10 to the 6 and 10 to the 6. So 6 plus 6 is 12. So down here, I've got 12. Well, now I've got, since I'm dividing, I subtract. So 15 minus 12 is 3. So I've got 10 to the 3. And I'm going to cross those off so I know not to use them again. All right, so next what I'm going to do is just take care of my coefficients, my numbers in front. Okay, so I've got my handy dandy calculator right here. Okay, and the first number here is 6.67. So what I'm going to do is 6.67, and I'm going to multiply that by my 1.5. Then I'm going to multiply that by this number here. So multiply by 5.972. Okay, so all of that, I could hit equals here if I wanted to and get a number on the top, or I could just divide and then divide again. Okay, or I can divide by the square since they're the same numbers. So I'm going to say divide by 6.378, and I'm going to hit my square button, which is this one right here. So I'll hit the square button and equals. All right, so what I'm ending up with here is 1.467, because I'm going to round the 8 and the 8. Okay, so 1.467, and this is going to be newtons. Okay. So what this is saying here is that our force of gravity of this 150 kilogram person, the force of gravity is going to be 1,467 newtons. Okay, all right. But there's an easier way to do that, right? Well, what's the easier way to do that? We could have done this in terms of the force of gravity equals mg. Now remember what g was. Okay, so g was 9.8. Okay, so, or 9.81 if you want. So force of gravity is going to be 150 kilograms times 9.81 meters per second squared. Right? That's what we did earlier. That's what we did in a previous chapter. So the force of gravity is, and then we take our calculator again, and we do 150 times 9.81 equals, and I get 1,471, or 72 if we round the 5 to the 2. Okay, and this is going to be newtons. Now, they're not perfect, but they're off by just a little bit. And what do I mean by a little bit? Well, if I take this, I clear that, and I say 1,467, and I divide that by 1,471, okay, I get 0.997. So basically what I'm talking about is the difference between these two numbers is 0.3%. 0.3%. That is very good. Okay. Now, what can we do with this? Well, what I'm going to do is I'm going to say this. I'm going to slide this a little bit more. Okay. So what I'm going to do is I'm going to take the universal law of gravitation. So I'm going to say G m1 m2 divided by d squared. Okay. And I'm going to say that this is equal to mg, m1 g. Because remember, I put m1 as being the mass of 150 kilograms. So what does this do? Well, m1 and m1 cancel. So here, g is going to be equal to capital G m divided by d squared. So that's going to be my acceleration. So let's find out what this comes to. We know what it's supposed to come to. G should be equal to 9.81 meters per second squared. That's what it should be equal to. So let's find out what happens. I'm going to do this one in green also. Okay, so we've got G equals, and I'm going to do dimensional analysis one more time. So 6.67 times 10 to the negative 11 Newton meters squared divided by kilograms squared. And then I'm going to put in my numbers for the Earth. So 5.972 times 10 to the 24 kilograms. Then I'm going to put in my radius of the Earth, which is 6.378 times 10 to the 6 meters, and this is quantity squared. So I broke them apart last time, but this time I told you why I broke it apart. So this time I'm going to put them together. So now let's do our powers of 10 once again. So I'm going to say times 10, okay, and then we've got 24 minus 11, which gives us 13. Oops, I didn't want to put 13 there. I want to put it up at the top. So let me get rid of that. Okay, so I've got this guy and this guy cancel, so that's 13. And then here I've got 6 times 2, which is 12. So I've got 12 down here. And 13 minus 12 gives us a 1. Okay. Now let me take care of the coefficients in front. So here I've got 6.67 times 5.972 divided by 6.378 squared equals, okay, and I get 0.9792 if we want to put that in that too. Okay, so this is going to be newtons because kilograms cancel, meters cancel, and I'm left with newtons. Okay, so this is equal to G. Now let's clean it up because this is not proper scientific notation, but we don't need to. It's a 10 to the 1. 10 to the 1 is 10. Okay, so I multiply this number times 10, and my G equals 9.79. And this is meters per second squared. Okay, so meters per second squared. Okay, because this is kilograms squared. It's going to cancel. There's going to be stuff there. Okay, so meters per second squared. But if I clean this up a little bit more, that makes this 9.8. Okay, so gravity of Earth is 9.8 meters per second squared, which is the number that we've been using until we got to a couple of those worksheets where we did 9.81. Okay, all right, so this is why we use 9.81 instead of using the entire equation for the universal law of gravitation. Okay, but we can use the universal law of gravitation for forces like the moon and the earth and Jupiter and the earth and how they pull on each other from the distances they are. Uh, if we take the distance here and we have a satellite in space, well, we just add the distance of the satellite here and then we square it. So it's still, I mean, we still need the mass of the satellite. If we want to know how much gravity we're going to feel if we're up in space, then we would add that distance. Okay? So this universal law of gravitation works for several different pieces. Okay, but I wanted to show you this, that these two numbers, that's not magic that we got this number. Okay, the universal law of gravitation helped us with it.